In this chapter, we have Reynolds number and geometry effects. The technique of boundary layer. BL analysis can be used to compute viscous effects near solid walls and to patch these onto the outer inviscid motion. Compute viscous effects near solid walls. And to patch these onto the outer inviscid motion. These the outer inviscid motion. This patching is more successful as the body Reynolds number becomes larger, as shown in this picture. This picture provides, for example, this picture shows a uniform string U move parallel to a sharp flat plate of length L, as shown in this picture. If the Reynolds number, Reynolds number is U velocity L on the kinematic viscosity is low in the picture A. The viscous region is very broad and extends for ahead and to the side of the plate. This viscous region in the low Reynolds number. So we can write for A. The viscous region is very broad. And extend far ahead and to the side of the plate. B the plate retards the oncoming stream greatly, and a small change in flow parameters cause large change in the pressure distribution along the plate in the figure A. Thus, although in principle it should be possible to patch the viscous and inviscid layer in a mathematical analysis, their interaction is strong and nonlinear. There is no existing simple theory for external flow analysis, and Reynolds number from 1 to, let's be right, There is no extending Reynolds theory existing. Simple theory for external flow analysis. And Reynolds numbers from one to about 1000. Such thin layer flow are typically studied by experimental or numerical modeling of the flow field on computer. So we have experimental and CFD application to solve this type of flow, very laminar flow with Reynolds between 1 and 1000. A high Reynolds number flow B. Let me provide picture here again to more description. A high Reynolds number flow in this picture is much more amenable to boundary layer patching as first pointed out by Prantl in Prantl. The viscose layer, either laminar or turbulent, are very thin, thinner even than the drawing shows. Here we define the boundary layer thickness delta. We can define boundary layer thickness delta as the locus of point where the velocity u parallel to the plate reaches 99% of external velocity u. As we shall see in the later chapter, the accepted formulas for the flight plate flow on their approximate range have a function, conditional function, which are to the boundary layer thickness function as a flow properties, and in this case Reynolds x. X is the point that we need to evaluate. turbulent for turbulent flow and laminar flow, we have a function for boundary layer thickness and the x direction point with a function of Reynolds x, where Reynolds x is Q(x) on nu. It's called the local Reynolds number. Of the flow along the plane surface. The turbulent flow formula applies for Reynolds is greater than approximately 10 power 6. Various calculation can be made from this formulation. The blank, maybe we don't have, for example, the boundary layer thickness for low Reynolds number. It depends on over the Reynolds number magnitude. For a slender body such as a plate and a force parallel to the oncoming stream, we conclude that this assumption of negligible interaction between the boundary layer and the outer pressure distribution is an excellent approximation. For a blunt body flow, however, even at a very high Reynolds number, there is a discrepancy in the viscous inviscid patching concept. Consider this picture to shows the sketch of the flow past a 2 or 3-dimensional blunt body. This figure provides two sketches of flow past a 2 or 3-dimensional blunt body into various Reynolds into same Reynolds number flow. In the idealized sketch, we have same Reynolds number for these two flows, but we have two type of assumption: idealized and the actual. In the first, there is a thin film of boundary layer about the body and a narrow sheet of viscous bed in the rear. About the body and a narrow sheet of viscous. The patching theory would be glorious for this picture, but it is false. In the actual flow, the boundary layer is thin on the front. The boundary layer is thin on the front or wind bar. Side of the body outside of the body as shown in this picture. Here in the actual flow, the boundary layer is thin or on the front or windward and side of the body, where the pressure decreases along the surface, where the pressure decreases along the surface. But in the near the boundary layer encounters increasing pressure, adverse pressure gradient. Let me write this is favorable pressure gradient. But we have here the adverse pressure gradient. Breaks off or separate into a broad pulsating wedge. The mainstream is affected by the wake. Mainstream is deflected by this switch. Wake, so that the external flow is quite different from the prediction from indice theory with the addition of a thin boundary layer. So the external flow extremely different from implicit assumption. There is an example related to this section. The next section is the momentum integral estimates in next video.